السلام عليكم ورحمة الله. بسم الله الرحمن الرحيم. My name is Abdurrahman Boudara, and in this video I will be introducing you briefly to the subject of my intervention that I will be presenting, inshallah, in the National Conference of Nonlinear Differential Equations and their applications in the upcoming 11th of February. The title of my presentation is Admissible Mappings and Fixed Point Results. Of course, I'm not going to go into too much detail in this video, but I believe I'll be able to answer questions on the day of the presentation. We will start with a brief introduction of the fixed point theory and multi-valued maps. Of course, what is our purpose here? Our purpose here is to discuss a few fixed point results that rely on alpha admissible mappings and theta contractions, which is a type of weak contraction we will get to later. Of course, fixed point theory is fairly known. It is a subfield of nonlinear functional analysis, first truly bloomed in 1922 when Stephen Banach came up with his first theory of fixed point to prove the existence and uniqueness of a fixed point in a metric space X. Of course, ever since then, there has been many new discoveries in this particular field. New theories and results have been found. Some of them were able to prove the existence of the fixed point, but some of and as well as the uniqueness, but some of them were only able to prove the existence of a fixed point and not its uniqueness. Now, what we'll be discussing today specifically is the concept of the fixed points in multi-valued maps. Now, of course, what is a multi-valued map? A multi-valued map is a map that is defined on a certain space, but its images are not, the images are not elements. They are subsets, to say. That is that one value, that is to say that one element can have multiple values as part of its image. Of course, when it comes to multi-valued maps, fixed point theory was always discussed in the setting of a single valued map, which makes sense because we have one value, and if that value isn't affected by our map, then we say that it is a fixed point. But the concept of the fixed point can also work in this for multi-valued maps, as we're about to see. From the first researchers who started this, we have Semets et al., who introduced the concept of alpha admissible mappings to multi-valued mappings, because before we only had alpha admissible mappings for single valued maps, but it was later expanded. And now that it's been expanded, we can also came up with similar fixed point results to the ones that relied on alpha admissible mappings when we were only discussing it in single valued maps, as we're about to see. Now, first, we're going to start with a few definitions so we can know exactly what we are about to deal with. Now, of course, we need to define what a multi-valued mapping is. Let's say we have X and Y that are two non-empty sets. T is a multi-valued mapping defined from X to P of Y. That is the family of non-empty subsets of Y. That is to say that each element of X has an image Tx by the mapping T. And Tx is not an element of Y, it is a subset of Y. And of course, single-valued maps are also multi-valued maps, since for any X, a singleton, the image of X is Y, which is a subset of Y that only has one element in it. Now, of course, A fixed point does exist for a multi-valued map. All we have to do is find an element X defined, an element X, of course, we are talking in the case of a multi-valued mapping that is defined from X to the family of non-empty subsets of X. So if X is an element of the subset Tx, then X is, of course, a fixed point of the multi-valued mapping T. So yeah, the concept of a fixed point exists for multi-valued mappings, just under a different meaning. Now, of course, here we're going to remind ourselves of a few key concepts, such as the concept of the distance between an element X and a subset A. Of course, when we are talking in a metric space, XD, the distance between an element X and a subset A is the inf of the distance between X and Y, so that Y is an element of A. Of course, the distance between X and phi is equal to infinite. And the distance between X and A, if X is an element of A, would be equal to 0. Also, an important theorem, if X is an element of the metric space X and A is an element of Kx, that is to say that A is a compact subset of X, then there exists an element X0 of A, such as that the distance between X and A is equal to the distance between X and X0. That is to say that this family of positive number right here does in fact reach its minimum. And now we are introduced to the function E. Now, of course, the function E is defined from CBX multiplied by CBX to R plus. Of course, CBX is the family of closed and bounded subsets of X. This function is defined as follows. E of A and B is equal to the superior of the distance between A and B, so that A is an element of the subset grand A. That is how we calculate E of the two subsets A and B, with the condition that A and B are both, as we said before, closed and bounded subsets of X. We need this function to define the next element. Of course, when we talk about multi-valued mapping, we're not going to talk about continuity in the same sense we talk about continuity with single-valued mappings. For multi-valued mappings, we have two important concepts: semi-continuity upper and semi-continuity lower. We say that a multi-valued mapping T is upper semi-continuous on a point x0 if the limit of E of the image of xn and the image of x0 when n tends towards infinity is equal to 0. And we say that it is lower semi-continuous on a point x0 if the limit of E of the image of x0 and the image of xn when n tends towards infinity is equal to 0. Of course, something important here, we need to understand that the function E is not a commutative function, okay? It does not commute. We cannot switch the two subsets A and B and obtain the same result. So it makes sense for these two concepts to be different from each other, unlike the concept of continuity for single-valued mappings. And of course, we can call a multi-valued mapping continuous if it is both upper semi-continuous and lower semi-continuous. That is how we define continuity for multi-valued mappings. Of course, something we need to understand here is the concept of alpha admissible mappings. This concept also exists for single valued mappings, but we will be concentrating on multi-valued mappings here. Of course, if we have xd, a metric space, and alpha, a function defined from x multiplied by x2 r plus, and we have T, a multi-valued mapping that is defined from X to the family of closed subsets of X, that is to say that all the images of elements of X are closed subsets, then we can say that T is an alpha admissible mapping if for each X of X and Y of the image of X, we in which case we have alpha xy is superior or equal to 1, we have alpha y and z is superior or equal to 1 for each z that belongs in the image of y. This is how we define an alpha admissible multi-valued mapping. Now we are introduced to a new type of mapping of metrics, that is the Pompey-Hausdorff metric. Now, what is the Pompey-Hausdorff metric? The Pompey-Hausdorff metric is a metric that is defined on the family of closed and bounded subsets of X. And it defines, with this family, it defines a metric space with all the qualities of a metric space. So how does this metric work exactly? The Hausdorff metric, the metric space, works as follows. The Hausdorff metric space of two closed and bounded subsets of X is equal to the maximum between E of A and B and E of B and A, because as we said before, these two elements are not the same because the function E does not always commute. And so if we have these two values, the greater one between the two will be the Hausdorff metric between the two subsets, the two closed and bounded subsets of X, A, and B. Now let theta be the set of all functions defined from 0 infinity to 1 infinity that satisfies the three following conditions. Theta is non-decreasing for each sequence Tn in 0 plus infinity. The limit of the image of Tn when n tends towards infinity is equal to 1 if and only if the limit of Tn when n tends towards infinity is equal to 0. And for the third condition, we have there exists a number r that is strictly superior to 0 and strictly inferior to 1, and an element L from 0 to infinity that can also be equal to positive infinity, such as that the limit of theta of t minus 1 divided by t to the power of r when t tends towards 0 with greater numbers is equal to the positive element L. And finally, we are introduced to the concept of an alpha theta contraction. Now, what is an alpha theta contraction? First, we need T, a multi-valued mapping defined from X to the family of closed and bounded subsets of X. All right, and we need alpha, a function. We define the set ST alpha by this formula. That is to say, it is a subset of the space X divided by X, in which for each pair XY of this subset, the image of the pair XY by the function alpha is strictly superior or equal to 1, and the Hausdorff metric between the image of X and the image of Y is strictly superior to 0. For simplicity, we're going to call this set S. Now, of course, note that for each pair XX, it's not going to be an element of the set S. Now, T is a multi-valued alpha theta contraction if there exists a function theta of the family theta and a number k that is strictly superior to 0 and strictly inferior to 1, such as that the image of the Hausdorff between tx and ty is strictly inferior to the image of the distance between x and y to the power of the number k. But this only applies to if the pair xy is an element of the set S. Now we can get to our actual results. We will now introduce one of the many theorems that have been introduced to prove the existence of the fixed point for a multi-valued mapping. We're going to start with the following lemma. This lemma suggests that if T is an upper semi-continuous multi-valued mapping, such as that Tx is closed for all elements x, it is a closed subset for all elements x, and if xn is a sequence that converges towards an element x0 and yn is a sequence that converges towards an element y0, and for each element xn, yn is going to be an element of the image of xn by the mapping T, then y0 would also be an element of the image of x0. This lemma will be very important later when we are about to prove the existence of our fixed point, as we're about to see in the following theorem. Now, the theorem goes as this. We have xd, of course, in metric space, and we have T that is defined from X to the family of compact subsets of X. It is a multi-valued mapping, and alpha is a function defined from X multiplied by X to 0 and plus infinity. Now, if the three following conditions hold, first condition, T is an alpha admissible multi-val and also a multi-valued alpha theta contraction, with theta being an element of the family theta. And there exists an element x0 of the metric space and an element x1 from the image of the element x0 by our mapping T, such as that alpha of the pair x0, x1 is strictly superior or equal to 1, and T is upper semi-continuous, then T has a fixed point. Of course, notice that we have mentioned that it has a fixed point, but we haven't declared whether it's unique or not. In order to prove that it is unique, we're going to need to add another condition, if possible, in the future. Now, we're going to prove this theorem. We will start our proof. Now, let's suppose that T has no fixed point. Then that would mean that the distance between each X and its image by the multi-valued mapping T is superior to 0. Now, for all X of the space X, let's take x0 and x1 be as mentioned in the previously discussed conditions. That is to say that, of course, that is to say that alpha of the pair x0, x1 is strictly superior to 1. And since we know that x1 is, of course, since we already know that x1 is part of the subset T x0, we can safely say that H Tx0 and Tx1 would be strictly superior to 0. And therefore, the pair x0 and x1 is an element of the set S. So, from the properties of the alpha theta contraction and the properties of the function theta, we obtain the following formula. Theta of the distance between x1 and t of x1 and would be and theta of the Hausdorff metric of the image of x0 and the image of x1. Of course, it will be inferior to theta of the distance between x0 and x1 to the power of the element k. Now, of course, we know that k is a number that is strictly superior to 0 and strictly inferior to 1. And since tx1 is compact, then there exists x0 in tx1, such as that the distance between x1 and x2 is equal to the distance between x1 and t of x1. Now, let's consider now this element x2 as the second element in the new sequence that we are about to start. Of course, the sequence that we will be later proven to be a Cauchy sequence. And of course, since we are in a complete metric space, we will be able to use this property to prove that it does in fact converge. Now, of course, from the previous property, we just replace this distance with this distance, and we obtain to the image of the distance between x1 and x2 with the function theta is inferior to the image of the metric, Hausdorff metric between the image of x0 and image of x1 by the mapping t, which is inferior to the image of the distance between x0 and x1 to the power of the number k. Moving on. Of course, since t is alpha admissible, we get that alpha between x0 and x1 is strictly superior to 1. And of course, x2 is an element of tx1. This way, we can use the exact same reasoning we used before to prove the same formula, but this time, instead of using x0 and x1, we use x1 and x2. And similarly, we can obtain a new element x3 that is an element of tx2, the image of x2, such that the distance between x2 and x3 is equal to the distance between x2 and the image of x2 by the mapping t. And now we are finally beginning to form this new sequence, xn. It is a sequence of elements in x such as that xn plus 1 is an element of the image of xn by the mapping t, and the pair xn plus 1 is an element of the set S for each normal number n. And of course, it verifies the following formula. Theta of the distance between xn and xn plus 2 would be inferior to theta of the distance between xn and xn minus 1 to the power of k. Now, we will denote dn as the distance between xn and xn plus 1. That is to give us a new sequence of positive, strictly positive elements. Of course, following this reasoning, we arrive at the conclusion that theta of dn is inferior to theta of dn minus 1 to the power of k. And by extension, it would be inferior to theta of dn minus 2 to the power of k squared. And then following the same reasoning, we arrive at theta of dn is inferior to theta of d0 to the power of k to the power of n for each normal number n. And if n tends towards infinity, then we obtain that the limit of t dn when n tends towards infinity is equal to 1. Please keep in mind that theta of dn is strictly superior to 1 because theta is defined from 0 infinity to 1 infinity. Of course, according to the other property of theta, this would imply that the limit of dn when n tends towards infinity is equal to 0. And so, according to the third property of theta, there exists a number r that is strictly superior to 0 and strictly inferior to 1, in which case L, which is an element that could be a strictly positive real number or plus infinity, such that the limit when n tends towards infinity of theta dn minus 1 divided by dn to the power of r is equal to L. Now, in the next step, we will follow a simple reasoning to prove that whether L is a positive, strictly positive real number or plus infinity, we can always arrive at the same conclusion. D equals, if L was a positive real number, we take D, a positive value that equals L divided by 2. Of course, from the definition of a limit, then there exists a number n, 0, so that for all n strictly superior to n0, we have theta of dn minus 1 divided by dn to the power of r minus L would be inferior to D. That is to say, the distance between the sequence and its limits will at some point be inferior to this positive number. This, of course, implies that for each number n that is superior to n0, theta of dn minus 1 divided by dn to the power of r would be strictly superior to L minus D, which equals D. This, in the end, would take us to the following conclusion. N multiplied by dn to the power of r is inferior to 1 divided by D multiplied by N multiplied by theta dN minus 1. And if L is infinite, we will take D a strictly positive value. And from the definition of a limit, there will exist, of course, a value n0, so that for each normal number n that is superior to this value, theta dn minus 1 divided by dn to the power of r would be superior to D. So we were always capable of reaching the same conclusion, whether L is a finite value or an infinite value. And now we will use this formula to prove that the sequence xn is in fact a Cauchy sequence. How will we do this? From this formula, we can reach this formula, of course, using what we have established before, that theta of dn is inferior to theta of d0 to the power of k to the power of n. We find that n in dn to the power of r will be inferior to a divided by n. A is, of course, 1 divided by d. A times n times theta dn to the power of k to the power of n minus 1, of course. And when n tends towards infinity, this would mean that the limit of n divided by dn to the power of r equals 0. Now, of course, according to the definition of a limit, then at some point, n in dn to the power of r will be inferior to 1, which means that dn, which is the distance between xn and xn plus 1, will be inferior to 1 divided by n to the power of 1 divided by r. Now, in order to prove that xn is a Cauchy sequence, we will take two random numbers, m and n, two normal numbers, m and n. The distance between xn and xm will equal the sum of the distance between each two elements that are, of course, each elements that are inferior to m or superior to n in their order. The distance between xn and xm plus, that is to say, the distance between xn and xm will be inferior to the distance between xn, xm plus 1 plus the distance between xm plus 1 and xm plus 2, all the way to the distance between xm minus 1 to xm. And of course, these are all elements of the sequence dn, and they are all inferior to the respective value 1 divided by e to the power of 1 divided by r. Now, we already know that this series, that is to say, e to the power of minus 1 divided by r being a number that is strictly superior to 0 and strictly inferior to 1, is a convergence series. And since it's convergence, this would mean that the series dn is also convergent, which means that the sequence dn would tend towards 0. This proves that xn is a Cauchy sequence, and since we are operating in the set of the complete metric space, this means that the sequence xn converges towards a point z. Now, of course, according to the previously established lemma, since T is an upper semi-continuous multi-valued mapping, then there we have Z being a member of TZ. Now, of course, this contradicts the assumption that T has no fixed points, and thus the assumption is false, which means that T does in fact have a fixed point. Now, of course, we could prove that this fixed point is unique, but we will need to add other conditions to our multi-valued mapping, and we can discuss those conditions in other theorems when we have the time, but unfortunately, I believe we've already exhausted most of it. Of course, in conclusion, this concept can be stretched much further because we already have so many fixed point results in the context of a single valued mapping. And the multi-valued mapping does in fact operate in a much similar way, but it does need to have those results adjusted, just like we did with the alpha admissible mappings, in order for us to be able to conclude new fixed point results for a multi-valued mapping. And of course, not only can we use this in the setting of a complete metric space, we can use a non-complete metric space or even a B-metric space if we have the correct conditions. Thank you very much for your time, and of course, special thanks to the people who worked on these works that have inspired today's presentation. Thank you very much.